In this episode, we focus on a skill that sits at the heart of ISEP thinking, being able to connect systems engineering and security engineering so smoothly that security never feels like a separate add-on. Beginners often imagine security as something you apply after a system is built, like putting a lock on a finished door, but systems engineering is about designing and managing a whole system from the start, and security is one of the system's essential qualities. When these disciplines are disconnected, you get the most common real-world failure patterns, like requirements that do not mention security, designs that cannot be secured without major rework, and late-stage testing that finds issues nobody budgeted time to fix. The exam is built to reward candidates who understand that security engineering must be integrated into the same lifecycle activities that guide performance, reliability, usability, and safety. That does not mean security takes over every decision. It means security becomes a normal part of how decisions are made and verified. Our goal is to build an intuitive, beginner-friendly picture of how the two processes align, where they share goals, and how to avoid the gaps where security tends to fall through. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good starting point is to understand what systems engineering is trying to accomplish at a high level. Systems engineering is a structured approach to defining what a system needs to do, designing a solution that meets those needs, building and integrating the components, and then proving the system works in its real environment over time. It emphasizes clear requirements, careful design, disciplined integration, and ongoing management of change because complex systems fail when decisions are not traceable and assumptions are not controlled. Security engineering shares those same disciplines, but it focuses on protecting the system's mission and assets against threats, failures, and misuse. Where systems engineering might ask whether the system delivers the right performance, security engineering asks whether it delivers that performance safely under adversarial and uncertain conditions. When you see them as two separate tracks, you create friction and late surprises. When you see them as two views of the same life cycle, security becomes a normal engineering concern that is handled early, revisited often, and supported with evidence. The first place the connection must be tight is in requirements, because requirements are the earliest point where you can prevent security gaps. Systems engineering requirements describe what the system must do, how well it must do it, and what constraints it must obey, such as safety rules, legal requirements, or interface commitments. Security requirements describe what must be true for the system to be trustworthy, such as who can access what, how data must be protected, and what evidence is needed to show the system is operating within acceptable risk. A common gap occurs when security requirements are written as vague goals, like be secure, rather than as specific statements that can guide design choices. Another gap happens when security requirements are treated as technical details rather than system constraints, which causes them to be ignored during architecture trade-offs. The exam often tests whether you understand that security requirements are part of the system requirement set and therefore must be elicited, refined, and validated like any other requirement. When security requirements are clear and testable, security engineering can connect naturally to design and verification. Once requirements exist, systems engineering moves toward architecture and design, and this is where security engineering must be present because the design phase creates the system's structure and trust boundaries. Architecture decisions determine what components exist, what interfaces connect them, where data flows, and what assumptions are made about users, networks, and dependencies. Security engineering connects here by identifying assets and threats, locating trust boundaries, and shaping design principles so that controls can be effective and assurance can be produced. A classic gap is designing interfaces for convenience without considering how untrusted inputs could influence high-trust logic, which leads to predictable failure modes later. Another gap is building a system that is too tightly coupled, where one compromise can cascade, because there was no deliberate separation of duties or segmentation of trust. Security engineering does not just add controls at this stage. It influences the design so that the system is easier to secure, monitor, and maintain. When you recognize that security is a property of the architecture, you stop treating security controls as decorations and start treating them as structural elements. Systems engineering also includes trade studies and decision analysis, which is a fancy way of saying you compare options and pick the best one based on criteria. This is an ideal place to integrate security engineering because it gives security a legitimate seat at the table alongside cost, schedule, performance, and maintainability. Security engineering contributes by translating security goals into criteria, such as reducing attack surface, improving resilience, or increasing confidence through evidence. A common gap is making trade decisions based only on performance and cost, then discovering later that the chosen approach cannot meet security needs without major redesign. Another gap is treating security as a blocker that says no, instead of as an engineering voice that helps shape safer options and clarifies risk trade-offs. The exam often rewards answers that incorporate security considerations into engineering decisions early, because that reduces downstream cost and improves assurance. When security is expressed as criteria and risk, it becomes part of rational decision-making instead of a last-minute argument. As the system moves into implementation and integration, the connection between the disciplines shifts from shaping design to controlling change and preserving intent. Systems engineering manages how components are built, integrated, and tested so that the final system matches the design and requirements. Security engineering connects by ensuring that security controls are implemented correctly, that secure configurations are baselined, and that integration does not create new trust pathways that were not intended. A common gap occurs when teams implement features that technically work but quietly violate security requirements, such as granting broad privileges for convenience during development and never tightening them later. Another gap occurs during integration, where two secure components become insecure when combined because their assumptions do not match, like one component trusting inputs that the other cannot validate. Security engineering helps here by focusing on interfaces, dependencies, and configuration baselines, because integration is where hidden assumptions become real behavior. On the exam, questions may describe systems that were secure in design but drifted during build and integration, and the right thinking often involves disciplined configuration management and verification activities. Verification and validation are where the connection becomes visible as evidence. And this is a big theme for ISEP because security must be provable, not just believed. Verification checks whether the system meets specified requirements, while validation checks whether the system meets real needs in real use. Systems engineering uses verification and validation to build confidence that the system works and is fit for purpose, and security engineering uses them to build confidence that security requirements are met and that the system behaves safely under realistic threats and misuse. A common gap is focusing on functional testing and treating security testing as a separate event at the end, which often misses architectural trust issues and creates a scramble. Another gap is collecting test results without traceability, meaning you cannot connect evidence back to specific requirements and decisions, which weakens assurance. Security engineering connects by defining what evidence is needed, ensuring tests and analyses cover security requirements, and supporting traceability so that confidence can be justified. Exam questions frequently test whether you can choose assurance activities that align with requirements and lifecycle stage, rather than defaulting to generic testing ideas. Systems engineering continues beyond deployment because real systems change, and security engineering must remain connected during operations and maintenance. Operations includes monitoring, incident response, patching, access management, and adapting to new threats, while maintenance includes planned upgrades and changes that evolve the system. A key gap occurs when a system is authorized or accepted once and then treated as permanently safe, even as it changes and its environment changes. Security engineering prevents that gap by emphasizing continuous monitoring, controlled change, and ongoing risk assessment, so assurance is maintained over time. Another gap occurs when operational teams make urgent changes for availability without understanding the security impact, which can undermine baselines and destroy traceability. Connecting the disciplines means maintaining the engineering intent through disciplined processes, So changes are evaluated against requirements and risks, and evidence is updated as the system evolves. On the exam, scenarios about drift, repeated incidents, or loss of visibility often point toward failures in ongoing engineering discipline, not just missing controls. A practical way to think about connecting the processes is to focus on artifacts and decisions that must remain aligned across the lifecycle. Requirements must connect to architecture. Architecture must connect to implementation choices. Implementation must connect to configuration baselines. Baselines must connect to verification evidence, and evidence must connect to operational monitoring. Each connection is a place where gaps can form if people treat documents and decisions as one-time events rather than as living commitments. Security engineering adds specific content to these artifacts, like threat-informed requirements, boundary-focused design constraints, assurance plans, and monitoring expectations. Systems engineering provides the structure and discipline that keep those artifacts meaningful, like traceability, version control, and controlled change processes. Beginners sometimes think paperwork is the goal, but in engineering the goal is consistency. The system you build and operate should match the system you intended to build, and security should remain intact across change. The exam often rewards a focus on traceability and lifecycle alignment, because that is what prevents security from degrading quietly. It is also important to understand the human and organizational side of this connection, because processes only work when roles and responsibilities are clear. Systems engineering often involves project managers, architects, developers, testers, operators, and stakeholders, each with different priorities. Security engineering adds roles that focus on risk, controls, assurance, and compliance, but those roles must be integrated into decision-making rather than isolated. A common gap is when security is treated as an external reviewer who appears late and says no, which creates conflict and encourages teams to hide problems. A better integration is when security participates early, helps define requirements, and supports design decisions with clear reasoning and evidence needs. That approach builds trust and makes security a partner in delivery rather than an obstacle. Exam questions sometimes test whether you understand how to integrate security into governance and project processes, because technical excellence is not enough if the organization cannot make accountable decisions. As we close, the main idea is that systems engineering and security engineering are strongest when they share a life cycle, a set of artifacts, and a discipline of traceability that keeps intent connected to reality. Security fits naturally into systems engineering when security requirements are treated like real requirements, when architecture is shaped by trust boundaries and threat-informed constraints, and when trade decisions include security criteria and risk. The connection continues through implementation and integration by controlling change, preserving baselines, and testing not just functionality, but also security behavior and assurance evidence. It continues through operations by maintaining monitoring, managing updates with discipline, and keeping risk decisions accountable as the system evolves. The gaps we want to avoid are always the same in spirit: vague requirements, late security involvement, uncontrolled change, and weak evidence. If you can describe how security threads through the same lifecycle steps as the system itself, you will be thinking in the way ISEP expects, and you will be able to answer questions that ask for the most defensible engineering approach rather than the most impressive-sounding control.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.